All right, welcome. Hi, everyone. Happy Monday. Today's plan is to continue working in chapter 3. So I don't want to move on to new material, just keep on doing permutation tests and make sure we get some practice on that. So don't forget, homework is due tonight, and then you've got your next homework assignment is posted due next Monday. And that is going to cover chapter 3. So it's going to cover permutation tests, which means it's going to be a lot of work in R. So for this next homework assignment, it's going to be required that you submit your work in R Markdown. So that was the point of the video, is just to get you acclimated with R Markdown. We'll do work in it today. So if you are having some kinks with R Markdown, we'll figure it out today and make sure that things are working smoothly for you. So we'll get to this R Markdown file. This is posted up in Canvas, so if you want to download that, we'll be working with that shortly. But before we get going, any questions with things? Life going well for you all? I hope. Good. So yeah, well, I don't know if you guys are keeping up, but it seems like we'll have somewhat more normal campus life in the fall, so that's nice. I think most of the math classes, in case you're curious, that we're going to be offering in the fall, most of them will be in person. Yeah, but we'll deal with registration later this month. Okay, so if there aren't any questions, then let's pick up with where we left things last time. So we were doing permutation tests, differences for means, variance, proportion were some examples that we looked at. And then we got to this example, which is on this worksheet we were doing last time. So this is worksheet 10 with permutation tests, where we were looking at this data set, which involved 12 swimmers who swam with this new wetsuit. They swam with, I imagine, a more traditional wetsuit, and they recorded their maximum speed in each of the bathing suits. And so they were curious whether the wetsuit made people swim faster. And so we basically got to the point where we set up the hypotheses, but we didn't get too much further than that. So the hypotheses here would be the swimsuit doesn't make a difference versus the swimsuit did help people swim faster. So we do have a direction implied here. Not that the swimsuit was different here. We really want to test that it made people swim faster. Any questions about those hypotheses? And so what's going on in the table is, right, we have their velocity for the new wetsuit, velocity without that wetsuit, and then we can see here's the difference in their velocities. And we were kind of talking about how can we set up a permutation test for this data. And so if we were to just use the process that we were working with last time, remember that process says, let's pool all of the data together. So that would be like, I just wrote out all 24 of those values. And then we randomly pick 12 of them to be like our fake wetsuit group. So what we're assuming here is that we're going to set up this process based on the assumption that there's no difference between these two groups. So the fact that one of them was wearing a wetsuit, some of these values were not wearing a wetsuit, the difference in these velocities is nothing more than just randomness alone. So with that in mind, we would just treat them all the same and then look at, well, what are the possible differences that we get when we just split these people randomly into two different groups. So let's just say I go through this process, pull all the samples together, then what we tell R to do is randomly select our wetsuit group, for example. And I just highlighted 12 values at random and listed them over here. So we would pick 12 values, calculate this mean, this winds up being 1.39. It would take all of the rest of them that weren't picked, say they're our control group, and it calculates a mean for that group of 1.54. And then we could compare these two. And based on this, we can see, okay, the control groups seem to have a higher average. So what's dangerous about this process? This is not how we want to do it in this particular example. Does anyone see why that might be problematic? Okay, let's set up some breakout rooms for you guys to think about that. Okay, go into your breakout rooms and just think about how we split these up. Think about whether that looks good. Think about what sort of problems there might be in that process. So there's 2 rooms. Ewell is in one of them. I'll jump in the other one. Think that at least the group that I was in talking with got to the gist of it. I don't know what happened in the other room. Where did you guys get in the other discussion room?
So if we don't have a matched up for each person, then we're not going to be getting like a true difference, because it's not each the difference in time is not matched up to the same person.
That's right.
Variation in the people's like ability to swim fast and body types that will affect their times.
That's right. So the fact that like this person has a 1.64 max velocity without this fancy wetsuit compared to this person who has a really has a slower speed with the wetsuit, right? Comparing these 2 values doesn't really tell me anything, right? Other than like this person swims faster than this person, right? Not anything about the wetsuit necessarily. So in the previous examples, there was no like natural structure to the data. It was just, here's a bunch of values. Now there is a structure that we have values in pairs. So we make sense out of this by comparing it to this. And so when we reshuffle our samples, we don't want to break up this pair. We don't want to break up this pair and so on. So instead, what we're going to do is, our assumption here is that this wetsuit doesn't make any difference. So in other words, the fact that this was 1.57 and this was 1.49 is just due to randomness and not the wetsuit. So in other words, it is just as well could have been 1.49 up here and 1.57 down here. So what we're going to permute is, for each person, we're going to just randomly assign one of those values to be the wetsuit, one of those values to be the no wetsuit one. And basically we flip a coin. We say 1.57, you are not the wetsuit time, 1.49, therefore you're the wetsuit. And then we look at all of the corresponding differences just by randomly permuting each of those pairs. So we're just going to permute things pairwise. And if you think about it, the only difference between assigning things this way versus this way is this has a positive difference and this has a negative difference, but it's the same amount. So when we set up this permutation distribution, what we're going to do is, for each of these pairs, we're randomly going to pick either a positive difference or a negative difference. So that's going to preserve the fact that there is a difference in each of these pairs, but that difference is random. It could have just as well have happened if we switched them around. So this whole process works when we have independent samples. So when we have 2 kind of independent samples, then this permutation process works by pooling them together. This is a case of, I'm throwing my pen. This is a case of matched pairs over here. So this is what we would call matched pairs. So here we're going to have a different process because we want to preserve the fact that these data come in pairs. So when we state these hypotheses, so let me just pause there. Any questions about kind of the logic involved in this process? So when we state these hypotheses, we state them in terms of population parameters. And the parameter that we're going to use here is called mu with a subscript of difference. So the null hypothesis is going to be that this difference is 0. And the alternative is going to be that wetsuit speed minus no wetsuit speed. The mean of these differences is going to be positive. And by difference, what it means is looking at the difference in the maximum speed for the wetsuit versus the no wetsuit. So this is referring to population, right? Like if every single person were to swim once without the wetsuit and swim once with the wetsuit, we could observe all these differences. So this is in regards to everyone in the population, which we don't have access to that data. So instead, we're just going to use the small sample that we have to assess which of these things is likely to be more likely to be true. So our test statistic here is going to equal, all of the mean of these differences. So we would add up those 12 differences and then divide by 12. So that's what the subscript difference is referring to. And we'll do these calculations with R, but I just want to kind of set up the stage before we jump into R. So any questions about that? Okay, then I would say go ahead and open up R Studio, and you guys are going to have some group work to practice this. So definitely the R Studio part is not an optional piece. Hopefully you're on a computer that has it. And it's hard for me to, maybe let me do it like this. Let me share my desktop. Okay. Is this large enough for you guys to see, or I can zoom in more? If anybody wants me to zoom in, I can do that, for example. Is that any better, worse? Okay. So I've got a couple of things opened up here. This is an R Markdown file for these practice problems. And in case you're curious, I created an R Markdown file. These were all of the problems that we worked out together last time. So the beer wings problem and so on. So I went ahead and typed up all of our solutions just so you have a sense of like, here's how you can use R Markdown, putting in our chunk codes and then putting in explanations along the way. And so you should be able to open up this one. This is what we did last time and use the knit button. And it takes a while. You'll see this might take a couple of minutes to run, but then it should open up in an HTML file. So with it, there any kind of questions you guys have about R Markdown? Any issues that came up? And so it takes a while to do this because it's like doing like 3 or 4 permutation tests right now. It's doing all of them that we did last time. So I would say, you guys are welcome to manage your own workflow about how you like working with R in R Markdown. For me personally, I like to do things in just R and just focus on the code. And once I know the code is working, then I'll go ahead and copy and paste parts of the code into R Markdown. Since with R Markdown, you have to run the whole thing at once, right? And so it's going to do all of these problems at once. It just, you saw how long it took my computer to do it. Then you get this nice HTML document with your R code and the corresponding output there. So these are all the problems we did last time. So yeah, so we did the hot wings problem. Here was the permutation distribution. There was the picture, there was the p-value, and so on. So I would definitely encourage you guys to go through this if you haven't. And I added some kind of like editorial comments here about why we did certain things in the code that might not have been in the other solutions that we had. So I would definitely say this could be a good source of reference when you're working on the homework problems. So when you guys are submitting your next homework, you're welcome to use R Markdown for this assignment if you like it, the one that's due tonight. But for the next one, you guys are going to submit two things, R Markdown file and the HTML file that you get from it. But the nice thing about this is when you share an R Markdown file, right, somebody else should just be able to pick it up, knit it, and get the same exact output that you have.
So you don't want us to submit it as a PDF, you do want it HTML?
Yeah, HTML would be the preferred way just because those files are the most universal, I think. Sometimes PDFs might behave one way with one PDF viewer and another way with another.
Okay.
So I would say probably the more common way if you're sharing documents is to do it with HTML. And if someone has your R Markdown and they want to create a Word document for it, they can tweak it easy enough if they want to. Yeah. Yeah, so so HTML is preferred for me. Okay, so here's the file that we're going to work with today. So this is the permutation test practice. And so I typed in the problem and the solutions here for this one at least. And then there's a similar one that I would like you guys to work on that I just kind of left the outline of the questions, and you guys can fill in the answers in the space below these. So for this Olympic swimsuit problem, there's no data set in resample data. So I don't need to load that library. But what I do need to do is hand enter that data. There were 12 values in each of those. So here's our hypotheses. And in case you're wondering what these things do, they allow me to put subscripts on things in R Markdown. And so what's really useful to keep an eye on, I don't think you can see all the way up to the top of my screen, but if you click on the help menu, you can at least see some of it come down now. At the top, then there's a really nice file called Markdown Quick Reference. If you open up that, I would highly recommend having this open while you're working in R Markdown, because this tells you how to do the most common things that you would want to do. And so one of them is subscripts and superscripts. So that's where that's coming from. So we've got our null, our alternative hypothesis. And the next thing to do would be to calculate this observed test statistic, which should be the mean of the differences. So what I did here, what you're looking at in this file is, here are the 12 values for the wetsuit velocities. Here are the 12 values for the control group. And it's really important here that you order things correctly, right? Because these are pairs. So this and this correspond to one person. This is person two, that, I'm saying this and this. I don't know, can you see my cursor when I move it around? Yeah, good. I don't have a pointer. So the ordering matters here. And now I can create a vector by looking at the difference of these two things. So this difference vector is going to take all of these differences pairwise. So it's basically like that third row that we had in the table. And I'm going to save this. This is my observed test statistic to observed. And in case you're curious, there's a file also up in Canvas called matched pair swimsuit that, here it is, that just has the R code here and not the kind of commentary. And so what's nice is, at least when I'm compiling R, I can do it bit by bit, and I don't need to do it all at once. So this was a pretty quick calculation. I can see down here that the observed difference is 0.0775. Whereas if I knit this file here, it's going to do this and all of the other R code chunks that come after it. So what I like to do is use R as like my kind of my sandbox here, like my test thing to make sure that code works over here. Once I make sure it's working good, then I can paste it in over here. Okay, so any questions about this part of the process? And again, these C's over here just mean that this is a vector of data. So R organizes vectors as column vectors. It just means a column vector of data. Okay, so here's the new part of this process. So here's always the kind of the meat of these codes is how we set up the permutation distribution. So we're gonna, do the same sort of thing. This is how many samples we're gonna create, and this is where we're gonna store each of these permutation samples. And we're gonna have a for loop. And this we can call whatever we want. This is some vector that I'm gonna create. And what this does, this is gonna create we're going to randomly pick 1 or -1 12 different times. So this is telling us what are we randomly picking from. So in this case, we're just picking between one of two numbers, -1 and +1. This part here is saying how many things are we picking. We're going to pick 12. And here we are changing this option to replace with true, right? When we were doing the pooled sample process, we wanted to pick without replacement. Here, we only have two things to pick. So each time I pick a sign, I want to put it back in so that I can pick either positive and negative for the next one. So this, this matrix sign, right, it would look like 1, -1, 1, 1, -1, and so on, right? So it's just a vector of plus or minus ones, and those are randomly being picked each time. So now we're going to take this vector of plus or -1 and multiply it by this vector of differences. So this is like the last row in our table, and now we're going to randomly assign those differences to be positive or negative. So diff2 is like a permutation resample. So it's randomly giving pluses or minuses, and after we randomly assign those pluses or minuses, now we calculate their mean to get the new mean difference. And then we repeat this like 100,000 times. And then down here, we create our histogram. So we're going to plot this vector of results, and we're going to plot our observed difference in that as well. So that's what these two lines are doing. Any questions about that part of the code? So I'll run that over here in R just to see what we get. Yeah, and this is why it's a lot faster doing it in R than it is in R Markdown, since I can do it one at a time. So here is my permutation distribution. Our observed difference was like 0.07. And so we can see here, that is one of the more extreme differences that we got. And so now the p-value, this is a one-tailed test, since we assumed in the alternative that the swimsuit was making you swim faster. So now the p-value is going to be, out of all of these 100,000 samples, how many of them were as or more extreme than the one we got? And that's what this over here is calculating. So again, the things that you're going to want to be careful about with this code is sometimes we need to put a 2 here if we have a two-tailed test, and sometimes we need to change the direction of this inequality depending on whether our observed value is positive or negative. Since we have an observed difference, which is positive, things that are going to be more extreme are going to have to be even more positive. And again, we've got one tail, so we don't want that. And now I'm going to just run this last line to get the p-value. And when you see things like this is scientific notation. So this means like 2 times 10 raised to the -4th. Well, it looks like that. So when you get things that have e to the -0.4, usually that means like really, really small. That makes sense, that we've got a p-value over here that seems to match the picture. You're bound to make mistakes at times, and that's totally fine. But I would encourage you to make sure that you compare the value that you get to the picture and make sure they're consistent with each other. And when they're not consistent, don't just ignore it, go back and try and fix it. So if I got a p-value that was like 0.8, I would know there's a problem because there's no way that 80% of the area is above that line, right? So that's what the p-value is telling me. Questions? So I'm going to knit this and just see what we've got. So yeah. I did not do this part over here. I forgot to put that in there. So I will pick this up and put it right over here. And that's how easy it is to kind of move our code from one to the other. And I don't really need this stuff over here. And I can interpret this by saying there is a, so I'm going to do the following. I'm going to assign this output to the thing called p-value. And we can do inline R code as well. So the inline R code is just one of those symbols. And just know that with inline R code, it doesn't show you the R code, it just shows you the output. So if I want to display the p-value as a percentage, I can just type this. And what this does is it takes the value that I just assigned up here, multiplies it by 100 to make it a percentage. And what's nice with inline code is that it kind of lets you input values that you've calculated previously in your R code. I did not close this off correctly because I could see this is shaded. It's really common to use the wrong apostrophe. I'll just say that. It's actually not an apostrophe that we're typing here. So basically all I'm saying here is that this is telling me how unlikely my sample is if the null hypothesis were true, which means that the swimsuit didn't help. And so I'm just going to knit this just to see what this document looks like. It's not a bad idea to save it. And then I'm going to knit it. This one shouldn't be too bad because there's only one permutation test in here. And so, yeah, we didn't need it for this one, but you will need it for the next example that you're going to work on. So it's always good to load the libraries as the very first thing, just so whoever you're sharing this with knows, oh, I don't have that package installed. I need to install that package before I run this code. But here you go. So here's our subscripts. And this is kind of what the output looks like. There are different ways you can format this. There are some different like style templates. I'll let you guys choose how hardcore you want to get into R Markdown. But at the basic, this is what it would look like. This is me putting no special formatting on anything. And so these, this inline R code over here, right, took this, the p-value got displayed better over here, took this value, right, I multiplied it by 100 to convert it to a percentage. And this R observed over here just got plopped in right here. So in these cases, you don't see the code, but you see the output of that code. Any questions? Okay, so what I'd like you guys to work on in groups is this problem here. So this is one of the exercises from the textbook. And so this data set, and if you're kind of curious, if you want to color code things, I like colors. You can do it with HTML tags if you're familiar with HTML. Otherwise, you can't get colors in here. So that shaded groceries green over here. So set up hypotheses. And so here the idea is they want to know, is there a difference in the price of groceries sold by Target and Walmart? And that again is a data set that is called groceries. So here's the solution. I don't want to get too deep into the solution, but let me just run this. And let's view the data set just to see what it looks like. Again, the data set is called groceries with a capital G. So they just took a sample of like 30 different items from a grocery store, from Walmart and Target. They compared the prices of the two. And so what we want to think about is, you know, who's cheaper overall, Walmart or Target? And so ideally, we could do this for every single item that both stores sell, but here's a sample of 30 of them. And again, I don't want to compare this price to this price because they're totally different things, right? So we want to preserve the fact that this value and this value belong together. So with that in mind, I'll have you guys just go into breakout rooms and try and set these up. So for this one, there's nothing more to do beyond type your hypotheses. These parts, B, C, and D, these are all going to require you to enter some R code. And it very well may be that you can go back up here, copy some of this code and tweak it down there would be my suggestion. But I'll leave it there. Is there any questions? Okay, so I will open up the same breakout rooms as last time. I think I can do that. So seems like stuff went well with the matched pair grocery problem from what I could see, but were there any questions that you guys want to bring up about that? Okay, so what I don't know is how far you might have gotten on the aquifer problem. So this is dealing with that Minnesota groundwater data set. And kind of the main point of it is not that important to get into the nitty gritty part of what types of aquifers there are out there. But the point here is that, you know, this was a data set where we had thousands of samples taken from water wells, and those water wells were fed by different aquifers. So what we might want to test is the lead level any different from waters being supplied by one aquifer compared to another? So in this, the statistical question here is they suspect that the lead levels are lower when the aquifer is buried beneath some rock as opposed to when the aquifer is above ground. So the hypotheses here would just be that the lead levels are the same versus it's lower than in the buried one than in the surface one. Any questions about the hypotheses? So in this case, this is not a matched pair, right? There's not a natural way of saying here was a well from this aquifer, here's another well from another aquifer. These are two independent samples. So when we go about this process, it's going to be similar to the way we did like the hot wings problem. So here's how we could kind of subset the data here. So this would involve subsetting the data. So over here, you can think about this as the pooled sample. So these are all of the lead levels that were in the water. I see. This is not what I want to do here. So this is a good example of I made a mistake. Our pooled samples should just contain data that has just these two buried quaternaries, right? The buried and the surface one. And if we actually go in and look at the data, you can see that there are other types of aquifers in here, right? And Cambrian is not at all kind of pre-Cambrian. These are not related to the question of comparing these two aquifers. So this is important because I realize you're going to have to do this for some of your homework problems, is that I want to subset the data to contain just this and ignore all of the others. So what I did here needs to be fixed. And what I want to do is enter an OR command over here. So I want to say if the aquifer group equals this, or if it equals this. And the way that we enter OR in R is just a vertical bar. So what this is going to do, it's going to go in and create a vector of the lead readings from just these two aquifer groups. Let me just run that down here. And now I can see that this contains like 610 entries, whereas like this contained 895. So it's good, right? I have filtered out these Cambrian and pre-Cambrian things are no longer in my data set. So keep that in mind. You're going to have to do a command like this on homework. So this OR command, we just put a vertical bar between them. This is going to pull off just the buried one. This is going to pull off just the surface one. And then this is going to calculate that observed difference. So we're out of time here, so I'll kind of stop here, but I'll put up the solutions to this. I want to just close with kind of one command that we haven't talked about in R, which is quite useful, is this length function. So we've been kind of using this, let's view the data, see how many observations are in there. And that's how we can know like how many things are in our pooled sample versus the non-pooled one. And so over here, you could actually, rather than enter in like the number corresponding to how many things were in lead, I can send that number to a variable that I call total and then enter that in over here. And then I can calculate how many observations were in the buried data set and enter that over here. So rather than enter the values, I'm entering a function to calculate those values and then putting the output of those functions in here. But I will put up the solutions to this. It's a file called lead permutation test. I realize I think I made a mistake in my code, so I need to fix that code there, and I'll upload a solution for you to check your work against that. But that's it for permutation tests. So hopefully this gets you going for the homework that will be due next week. On Monday, we'll start talking about chapter 4, which is sampling distributions. So that's what the quiz and video are on before we meet next time. And next time we'll be doing stuff mostly not in R, so we'll be kind of marking up one of those PDFs in class together. Okay, well, have a nice afternoon. If you guys have any questions, just feel free to reach out to you or myself. Otherwise, see you guys on Wednesday.
Thank you.
Thank you.
Yep, see you guys.